Hello everyone, welcome back to another IB Chemistry SL HL video 2025 specification. It's been a week, so let's get right back into the periodic table. I'll be covering spec points 3.1.3 and 3.1.4, so let's just get right into it. So, periodicity refers to trends in properties of the elements across a period and down a group. So let's start by introducing these trends. So the first trend is atomic radii. This is something which decreases across the period, and this happens because electrons are pulled tighter due to higher atomic mass or higher nuclear charge. Ionic radii links nicely into this, and in terms of metal ions, their radii decrease, so it decreases. For your non-metals, atomic radii increase, and this all has to do with how nuclear charge is spread across electrons, or in the case of non-metals, ionic radii increase as the same charge has to be spread across more electrons, and there are more electrons in an energy level in comparison to your metals. Now, second trend that we'll look into is the first ionization energy. So, first ionization energy. So the definition for this is the energy it takes to remove 1 mole of electrons from 1 mole of atoms in a gaseous state. So just draw a little something here. So here's a formula for what this would look like. And the successive ionization energies, so your second ionization energy is the energy to remove 1 mole of electrons from a mole of +1 ions. So ions or atoms which have already had electron taken from them, also in a gaseous state. And your third ionization energy will be the same thing, except that it's for your +2 ions, and so on and so forth. This is pretty self-explanatory. So the first ionization energy is a property which increases across the period. And this is because, yet again, nuclear charge increases as atomic mass is heavier. Think of it almost as gravity. And you have a set amount of gravity that you distribute amongst your electrons. And that set amount is your atomic mass, that's your nuclear charge. And the more nuclear charge, the more atomic mass you have, the stronger this force is going to act, the closer your electrons are going to be pulled in towards the nucleus. And the more electrons that you have to spread this out by or divide it to, the less strong this force is. So, ionization energy increases across the period, but it decreases down the group. And this is simply because electrons are further from the nucleus, and lower energy levels block higher energy levels, and this is called shielding, so it prevents attraction. Another thing we need to know is electron affinity. So this is the energy released when a mole of electrons is attached to a mole of neutral atoms or molecules, also in your gaseous state. So our little formula for this looks kind of similar to the past one. You'll get something looking a little bit like that. And here X, this just represents any sort of element. And electron affinity, this is something which increases upward for the groups from left to right across the periods of a periodic table. So if you were to have your periodic table, right, let your bit stick out like that, lanthanoids, actinoids, it increases as you approach chlorine, but generally as you go up and right, you will see electron affinity increase. And this is because electrons added to energy levels become closer to the nucleus, yet again, more nuclear charge. So there's a stronger attraction between the nucleus and its electrons. Now, what else do we need to know? Electronegativity. Let's get right into that. So, electronegativity. Now this one is quite fun. So it's the ability of an atom to attract bonded electrons or pairs of bonded electrons to itself when in a covalent bond. Covalent bond. So if you were to draw this out, let's say, okay, we'll have fluorine and hydrogen. Let's draw this out for us. So fluorine, you'll have so this pair of electrons here is going to be pulled closer to fluorine, as this is the element which is the most electronegative. Non-metals generally are more electronegative than your metals. And let's just try to visualize this a little bit better. Well, let's say that we have 2 carbons here. Now each carbon will have its own s orbital, right? But what happens in electronegativity is that they essentially become one. We draw them together. And this is just your sigma orbital, or just s. And you can also get your polar orbitals, for example, carbon and oxygen, where you'll get your p orbitals, let's say the upper and the lower ones of the p, because we know that our p orbital does this on the y-axis, this on the x-axis, and then this on the z-axis. So we take this one and this one, that is what it will look like, and this is your polar orbital. And if we are to identify which side is the most electronegative, what we use is our delta symbol notation. So as oxygen is part of our electronegative triad, we know that this will attract bonded pairs of electrons more strongly towards it, so they will be further away from your carbon. So you would draw your delta negative symbol here. This tells us that this also has more energy than your carbon, which will be delta positive. And let's just look at one final little example of chloromethane. So chloromethane, just draw this quite nicely. Here we can see that we have an overall dipole moment, which means an overall unequal distribution of charges across the molecule. So your carbon here will also be delta positive, because chlorine is really quite electronegative in comparison to it, which means that this side of the molecule will be more positively charged compared to this one, which will be more negatively charged. And now chloromethane is quite volatile because of this. So as we said, polar molecule. And essentially, in terms of electronegativity, the closer you are to the element fluorine, the most electronegative of them all, the more electronegative it is. Electronegative triad. These are the three elements which are the most electronegative out of the periodic table, are nitrogen, oxygen, and fluorine. Just keep this in mind. But if anything, in your exams, you will have access to a periodic table in which the electronegativities of each element is stated. Now, elements with a overall difference in electronegativity over 1.8. So you subtract the largest by the smallest, and if the number that you get is more than 1.8, that means that you have an ionic bond on your hands. Now that is all for spec point 3.1.3. Let's get on to 3.1.4. Also, do just keep in mind that in terms of atomic radius, ionic radius, ionization energies, electron affinities, and electronegativity, you will have to know how to explain why there are these trends which are present in the periodic table. But if you ever do forget what the trend is, you do have access to periodic tables with this information in your chemistry little booklet that you'll be given in the exam. So now on to 3.1.4. Trends and properties of elements down a group include the increasing metallic character of group 1 elements and decreasing non-metallic character of group 17 elements. So let's just start off with our group 1 elements, our alkali metals. So alkali metals, these have low melting points due to electron shielding and decreased nuclear attraction. As they only have one valence electron, they tend to be very reactive and will easily lose this singular valence electron to have a full energy level, because full energy levels, full outer energy levels, equal stability. And these atoms, they tend to be quite large. So you got large atoms. And these metals, maybe you've seen videos or not, but they're actually quite soft. You could cut through most, if not all, alkali metals with a butter knife. They're really quite soft. And they also float in water. So these are your properties of alkali metals. So if you were to react an alkali metal with, say, water, this would be quite a violent reaction, and it will get more violent the further down the group you go, due to, as we said here earlier, electron shielding and less nuclear charge down the group, as energy levels are further away from the nucleus. But you will get a hydrogen plus a base. So this would look like, say, Na plus H. Your state symbols, can't forget those. And another thing we just need to know is that if you react an alkali metal with a halogen, which we will get into right after this, you will just get a salt. Salt. Yes, a salt. So reacting two sodiums with chlorine will get you NaCl, table salt. So halogen. Let's get into these. Let's get into halogens. So halogens are also very reactive, as they're only missing one electron to achieve a fuller energy level. These are also very electronegative, as they are on the far right of the periodic table. Due to their higher masses, due to their ability to have London dispersion forces, which is something we can get into in another video, London dispersion forces, they have a higher melting and boiling point. So your halide ions, let's just give us an example here. Cl2 plus 2Br minus gives you 2Cl minus plus Br2. Now, the reason why this charge here is changed is because chlorine, as it is a halogen, will take electrons from the bromine as the most reactive element, meaning that it will be the one with the negative charge, as it's just received these electrons to fill that outer energy level and be more stable. So your more reactive halogen takes from the halide, which then in turn actually makes itself a halide. How fun is that? And that is all we need to know for 3.1.3 and 3.1.4. Hope that was helpful and that this was in some way enjoyable too.